Greetings everyone. My name is Aniket Sabale. I'm a doctoral student in Biomedical Engineering Department at IIT Hyderabad. My topic for presentation is characterizing shear stress in soft tissue during HIFU sonication using finite element modeling. Diagnostic ultrasound modalities such as acoustic radiation force imaging, shear wave elastography uses low intensity ultrasound waves. These ultrasound waves interacts with tissue and creates acoustic radiation force which gives rise to shear waves. These shear waves are then post-processed to obtain relevant tissue information. The intensity of ultrasound waves in diagnostic ultrasound is significantly low, thereby the magnitude of acoustic radiation force produced is sufficiently low. In case of therapeutic ultrasound, the intensity of ultrasound waves ranges from few hundred to 10,000 watts per centimeter square. These high intensity ultrasound waves can produce sufficiently strong acoustic radiation force, which leads to generation of high magnitude shear stress. The shear stresses generated during HIFU applications in the vicinity of focal zone can possibly link to cause certain biological effects such as cellular death. Shear stresses generated can also possibly influence the drug delivery in the vicinity of HIFU treatment region. Therefore, it can be valuable to investigate the effect of shear stresses generated during HIFU applications. The goal of this study was to simulate hyposonications at different transmit frequency and at different focal acoustic pressure, which will act as a source of different magnitude shear stresses. The shear stresses and the tissue displacement in the vicinity of focal zone will then be quantified. A novel finite element model is developed to systematically assess shear stress generated during hyposonications. A single element concave shaped transducer of focal length 63.2 millimeters and aperture diameter of 33 millimeter is considered. The active area of the transducer is given surface pressure of varying pressure distribution, which resembles apodization and also reduces stress concentration effect due to discontinuity at the edges. The soft tissue material was modeled with hyperelastic neo-Wickel constitutive behavior with material properties as shown in table, which closely resembles to that of soft tissues in human. The soft tissue material model was extended with added damping material property, which will act as a absorber and avoids reflections from the boundaries. A 2D axisymmetric model was considered to save computational time and resources. A 5-cycle longitudinal wave was simulated at two frequencies, 500 kHz and 1.5 MHz, which corresponds to fundamental and third harmonic of the transducer under consideration. The surface pressure was selected such that they produce clinically relevant focal acoustic pressures. The animation shows longitudinal wave propagation for transmit frequency of 1.5 MHz at surface pressure of 5 MPa. At 35 microseconds, the longitudinal wave reaches focus, which implies speed of longitudinal wave as 1540 meters per second. After duration of 1 millisecond, the shear wave propagation could be observed propagating in a radially outward direction away from focus. Three node points at a distance of 2, 6 and 10 mm were considered and measurements were made. It was observed that at node points, the magnitude of displacement at transmit frequency of 500 kHz was higher as compared to 1.5 MHz case. Similar behavior of shear stress could be observed. This reason could be attributed that larger displacement of nodes leads to higher shear stress generation. It can also be observed that as the distance of node points increases away from focus, the magnitude of displacement reduces. The graph on the top panel shows peak shear stress obtained at node points for different operating parameters of the transducer. A pressure-dependent behavior of shear stress could be observed. As the surface pressure of transducer increases, the magnitude of shear stress is also increasing. The graph on the bottom panel shows time to peak obtained for the relevant shear stress. at node points. No pressure or frequency-dependent behavior could be observed. At all node points, the speed of shear wave was approximately 1.7 meters per second, which is equivalent to theoretical speed for the material under consideration. To conclude, we demonstrated that our proposed model could quantify the shear stresses generated in the vicinity of focal zone during HIFU sonications. This model could further be used to understand the effect of shear stresses at cellular level. I thank all the persons involved in the work at IIT Hyderabad and Medical Ultrasound Research Laboratory. Thank you very much.